to section 4.2. In this section, we are going to talk about the biggest use of the antiderivative, which you can see I have on the board here the definition. Let f of x be a continuous function on an interval a to b. The definite integral of f of x from a to b is given by, this is what's known as a Riemann sum. The limit as n goes to infinity from I equals 1 to n of f of xi delta x. Scary. We don't need this. What we need is to take this and interpret it in terms of antidifferentiation, aka integration. So you'll hear me say the word antiderivative or antidifferentiation. From now on, mostly what I'll be saying is integration. We're talking about the definite integral. So this sort of scary notation is just a way of taking a function over some interval a to b, and who knows what the function looks like, and it really only needs to be defined over the closed interval a to b. We don't really care about the rest of the stuff, but it could be there. That's fine too. And what it does is its application has us find what's known as the area under the curve. So what we're doing is we're taking a bunch of approximations like rectangles. I drew this function pretty flat here, but you'll see that as I come out here, I start to run into a problem. I hit the curve to approximate it. I'm kind of losing some area here. So if I want to approximate how much area is underneath this curve going to the x-axis, I run into a problem. I actually end up missing some space. Right? I don't calculate this when I just use rectangles. And why am I using rectangles? Well, because we know that the area of each one of these is just length times width, length times width, length times width. Right? So I say length times width. Maybe you mean length times height or width times height. Right? But you just take how long it is and how tall it is. You multiply those two numbers together, and you get each of these areas, but you miss some stuff underneath the curve. So what you want to do to try and improve this is you want to try and take the number of rectangles and let the number of rectangles you use go to an infinity, meaning you will start using an infinite number of rectangles. These rectangles will get thinner and thinner and thinner and thinner and thinner until there are an infinitely many number of them in here. And then you won't have so much of this stuff that you're missing. Right? In fact, you'll be calculating everything. If you let these rectangles get thin enough so that there are infinitely many of them in there, right? N number of rectangles and n goes to infinity, eventually you end up calculating the exact area under the curve. So this fancy notation, also known as a Riemann sum, is really the way we represent integration over a finite interval from a to b, starting here and going here. When I look at this function f of x, how much area is underneath that curve from start to finish. So this lets you add things up in terms of total area under the curve, and that is like the number one use for integration. Now, when it comes to algebra is very static. Right? You can always calculate the area of a circle. Right? There's formulas for it. Right? Area is pi r squared. You can always calculate the area of a rectangle. Right? It's just length times width. Right? You can always, even for three-dimensional objects, the volume of a cube. Right? If you have one side s, it's just s cubed. This side, and then however deep it is. But again, algebra is static. It is not moving. It is not changing. Whereas calculus studies the rate of change, which means when you study calculus, things are moving, things are growing, things are shrinking, right? And sometimes when we study these functions that have this weird curve defined by f of x, it's not a perfect triangle, it's not a perfect circle. Maybe it's an oval, maybe it's a triangle with a little piece cut out of it. That's when you need a much more general strategy in order to find the area for these things. So when it comes to finding area under the curve, that is like the number one priority that we want. when it comes to finding the antiderivative over a finite interval. So that's what we're going to practice. We're going to practice using that definite integral. But first, I want to show you the power of it. In situations where maybe we don't even know calculus, maybe there's a situation where we're trying to calculate the area just geometrically. Let's say we want to use geometry to calculate the area. Let's say we have, well, we'll go up to 5 here. 1, 2, 3. Let's say we have the constant function y equals 3, or f of x equals 3. That is the constant function y equals 3. And let's say we have this thing go from, let's go from 1 to 5. All right, so let's say we want to shade that in. So we want to find the shaded area. Pretty simple, right? I mean, it's just a rectangle, and hopefully the green shows up pretty well. All right, so it's just a rectangle. So if we want to find the area here, we just need to calculate its length and its width or height in this case, I guess if you look at it that way. So we'll say area is 5 minus 1 is 4, right? So it's 4 long, 1, 2, 3, 4 units, times its height. Well, its height, it goes from the x-axis up to 3, so it's 1, 2, 3 units. So it should be 12 square units. Now, nice thing about that is we can relate this concept of area to the antiderivative. This is our function, f of x, and we want to evaluate it from a to b. So a would be 1, b would be 5 with respect to x. That gives us the integral from 1 to 5 of the function 3 dx. And so I know this is a bit overkill in this situation because, of course, this is just a rectangle and we have formulas for finding areas of rectangles, but we know how to integrate this. Right? Don't worry about the bounds so much for now. First thing we want to do is just find the general antiderivative of 3. We'll get our x back, so it'll be 3x. Now, here's the beauty of the definite integral. We don't have to put on a generic plus c because we know exactly where our function is. We don't have to add or subtract some constant that we don't know is there. We know exactly where our function lives. So instead of tacking on some just random constant to, just kind of save our skin, we're going to evaluate this from x equals 1 to x equals 5. So when you see this vertical bar like this, that means evaluate from 1 to 5, right? From where we start to where we stop. Here's the process. We take the upper bound and we plug it in. So this upper bound is where we end. We take b and we plug it in 3 times 5, and then we subtract the lower bound, right? So we get rid of 3 times 1. Now what we're doing here is 15 minus 3, and we get exactly 12 square units. Right? And that's not a coincidence. Right? We didn't just randomly happen upon the same number. These two things are very intimately connected. The definite integral and the area are both very intimately connected. So again, that's the goal in this section, is to sort of look at these things geometrically, but start to relate them to their actual integral. And then in this section, they give you some nice geometric shapes that are, fairly easy to find the area without calculus. In the next section, they ramp it up, where they start giving you some different functions that we just don't have formulas for, right? Things like, cubic functions or x to the fifth plus x squared. You don't have a formula for that shape. And there are so many functions out there that you can't just have a cheat sheet that's infinitely long with every shape on it that tells you the area underneath that shape. So again, we have to be a little more general, and that's where the antiderivative kicks in. So let's take a look at find the area. Just using geometry. And we'll compare it to what we might have when we look at the integral. And let's take f of x equals 2x. So this function, y equals 2x, it's a linear function that's passing through the origin, and it has a slope of 2. Right, if I differentiate this, I get 2, so its rate of change is always 2, aka its slope is always 2. Go up one more there. So there is our function, and let's say we want to find the area from, we'll start at 0 and go to 2. Right, let's say we want to try and calculate this area. Now again, you can see if I used rectangles to try and approximate this shape, my rectangles would either be going above the curve or they'd be staying under the curve at some points. I'd get a good approximation, but I'd never get the exact area. But when we do that Riemann sum, which is actually the definite integral, the number of rectangles we use are infinite. They're infinitesimally thin, so I'm always just hitting the curve perfectly. Well, first let's look at this in terms of area, geometrically. So it is a triangle, right? So I want the area of a triangle, which is 1/2 the base times the height, which in our situation, that's just a static algebraic formula, right? That never changes. The area of a two-dimensional triangle is always going to be 1/2 the base times the height. So it's 1/2 times the base, which is 2. I'm going to use the x-axis here from 0 to 2. That has a length of 2. The height is 1, 2, 3, 4. The half and the 2 will cancel out, so I'll get 4 square units. Again, pretty easy to do once we see that picture. But again, just to reveal, the integration would allow me to integrate my function 2x from 0 to 2 to get this green shaded area. What would I do with this? Well, I'd find the antiderivative, which is x squared, and I will evaluate it from x equals 0 to x equals 2, which means I plug in the upper bound 2 first, and then I subtract the lower bound 0. It's the square function, so that's why I'm doing 2 squared minus 0 squared, which is 4 square units. Again, this is no coincidence. There is no magic happening here, just math. So the definite integral is going to provide us with a way of finding areas. Again, this is overkill. We don't need calculus for this static shape, and it's a shape that we've already known since geometry and algebra before this. So it's a bit overkill for now. So let's say we want to approximate the area under the curve. And let's pick on, I'm trying to think of a fun function here. put this f of x equals the square root of 4 minus x squared on the interval 0 to 2. Remember, this is just the interval notation, so that is our closed interval. And then they'll tell us use 4 equally sized subintervals. And use a geometric formula to find the exact area. Okay, so here is a situation where I'm looking at this function and I want to find the exact area. I would integrate from 0 to 2, but guess what? We cannot integrate this function, right? The square root of 4 minus x squared, we can't integrate it. I mean, it can be integrated using some more techniques, but we cannot integrate this function. We do not have the tools to integrate this function. So although integration is very powerful, sometimes even integration can leave you hanging. Well, what is this shape? What does this shape look like? You can put this function in your calculator. You'll get the upper half of a circle with radius 2. So if we want to look at this geometrically, and we really only want to go from 0 to 2, so we only need the stuff in the first quadrant. If you were to graph this whole thing in general on your calculator, you would get the upper half of a circle, right? But we don't really want the rest of it. We just want everything from 0 to 2. Which means we're trying to approximate this area. Let me get this guy a little more in the middle here. There we go. So when we look at something like this, and we want to try and approximate the area, first it asks us to use 4 equally sized subintervals, which means we would have to break this up into 4 subintervals. Now the length of this interval, length of A to B, is 2 minus 0, which is 2. So if I want to chop that up into 4 equally sized subintervals, then I want to take 2 and divide it by 4 to get 1/2 for my subintervals, which means I'm going to chop this up so that it starts here and goes to here. There's 1 subinterval, goes from 1/2 to 1. There's another subinterval, goes from 1 to 3/2. There's another subinterval, and then goes from 3/2 to 2. There's subinterval 1. There's subinterval 2, there's subinterval 3, there's subinterval 4. Now when I start to approximate this, my rectangles, I have a choice of going with either left endpoints, which means I'm going to take the left endpoint of the, or sorry, not triangles, I said triangles, rectangles, and I'm going to use the left endpoint to hit the curve. I'm going to use the left endpoint to hit the curve. I'm going to use the left endpoint to hit the curve. I'm going to use the left endpoint of each subinterval to hit that curve. Now you can see right away this is going to be a gross over approximation. I'm finding all the area under the upper half of the circle and then some little extra. I'm taking all the area under and then finding more, all this area and then finding more, all this area and then finding a lot more. There's too much, right? So I'm finding the area, but I'm overshooting, overshooting, overshooting. Another way that we can look at this, and I'm not going to do it both ways, but we'll pick one, and you'll see neither of them will be perfect. But if we look at this in terms of what we call right endpoints, then when I break these subintervals up, I still have 1, 2, 3, 4 subintervals. 1, 2, 3, 4. But when I look at right endpoints, I'm going to use the right endpoint of the rectangle, the right endpoint of the rectangle with my subintervals, the right endpoint of the rectangle with my subintervals. Ooh, unfortunately, the right endpoint is actually at 0, so there's no height. Now you can see I'm missing a bunch of area, missing a bunch of area, missing a bunch of area, missing a bunch of area. So that is a gross under approximation of the area. So 1 is too much. The left endpoints, this gave me too much. The right endpoints, that gave me too little. There is a third option that we have, and that third option is what we call using the midpoints. So again, we don't really care about that side, but this is the side we care about. If we want to use the midpoint, then we want to break this up into 4 subintervals, again, just because it's telling us to. Now we would look for a rectangle that hits the curve in the middle of the top of the rectangle. And it comes up and it hits the curve in the middle of that rectangle. Comes up, hits the curve, a little too high there. There we go, in the middle. Comes up, hits the curve in the middle. So now with this, it's a little hard to see here, but I'm getting some of the stuff under the curve that I'm missing, but I'm also getting some of the stuff above the curve. So I'm simultaneously over approximating and under approximating. If I were to look at this rectangle and the midpoint and where the curve passes through it, again, notice here I'd be getting extra area, or sorry, here I'd be like missing some area, but then over here I'd be getting extra area. So it's almost like the two balance each other out. Like I said, almost like the two balance each other out. They don't perfectly balance each other out because the shape of this curve, it's not a straight line. So these aren't just triangles with the same size. The curve is steeper over here than it is over here, so that shape might be a little bigger. So it all depends on the function when you do it that way. So if we want to try and approximate this, I'm not going to do it 3 different ways. We'll pick a way to approximate it, and my math lab in the book will tell you which way they want you to approximate it. The only thing that's different with the midpoints is you have to find the average between these two. All right, so if these were my left endpoints, I would use the endpoints 0. Left endpoint would be 0. Left endpoint would be a half. Left endpoint would be 1. Left endpoint 3 halves. All right, so you only need the left endpoints. Notice 2 is a right endpoint. We don't need it. But if you use the right endpoints, you would need 1 half, 1, 3 halves, 2. All right, so these would be your right endpoints. Notice you'd never actually use the 0 because that's a left endpoint. Here it's a little harder. You have to find the average between these two. And by average, I mean, just a standard mean. Take 1 half, chop it in 1 half. You need to now cook up the number 1/4. Take 1, add a half, divided by 2, you'll get 3/4. Here you'll get 5/4. Here you'll get 7/4. And then 8/4 is 2, right? So you've got to go hunting for these average values between the left and the right endpoint, which is just simply adding these two numbers, chopping it in half. Adding these two numbers, chopping it in half, right? Just add the subintervals, but take an extra half to get halfway out the halfway point. So let's try and approximate it. And since we did the left endpoints first, maybe I'll just stick with the left endpoints. You can see why we want to get away from this as quick as possible, because this is a lot of work just to get an approximate answer. It doesn't even give us the exact answer. It doesn't even give us the right answer. It just gives us an approximation. So here's my half subintervals. I'm going to approximate the area, which means I need to find the size of every one of these rectangles. Now this rectangle right here has a length of 1/2, right? I'm 4 subintervals from 0 to 2. So I chop that up into 4 subintervals. I go from 0 to 1/2, and then I go from 1/2 up to here, back to 0. So there's my first rectangle. And that first rectangle is hitting that left endpoint. Where is that value? How tall is this rectangle? Well, it's 1/2 wide. And the area of this rectangle is going to be given by its height. Since I'm using the left endpoint, I need to find f of 0. That'll put me on the curve. Same thing with the next rectangle. I need to know the width. Well, the width is still going to be 1/2, because from 1/2 to 1, that width of that rectangle is 1/2. And now I need to figure out how high that rectangle is. Well, I'm using the left endpoint, so it's got to hit the curve when x is 1/2. So it's still going to be adding on this whole other area that's 1/2 times f of 1/2. Same thing with the third rectangle. It's 1/2 wide, but where does it hit the curve? That's the height of this rectangle. Well, it hits the curve at f of 1. So that means I need to go find f of 1 and multiply it by the width, 1/2. Last but not least, this very last one, it is 1/2 wide, but it has a height of f of 3/2. That's where it hits this left endpoint. So it's 1/2 times f of 3/2. Okay, so these are not going to be the nicest numbers, except maybe, f of 0 is 2, because we can see it's the upper half of a circle with radius 2. But we can see that 1/2 is a common factor everywhere. So what we can do is we can factor out that 1/2 from each one of these terms. And now concern ourselves with multiplying 1/2 by whatever all this stuff is. Now, let's just take it to, we'll take it to a couple of decimal places here, because these are not going to be the nicest numbers, except the first one. F of 0 is 2. F of 1/2 is about 1.93649. F of 1 is about 1.73205. Oops, that's smudge in there. And f of 3/2 is 1.32288. No, I'm not doing that in my head. That would be a little bit too much, in my opinion. But we can approximate them with the calculator. And then we can do 1/2 times, this number is approximately 6.99142. Just to save the space, let's do 3.49571. Okay, that's an approximation of how much area is there. Now, it's definitely an over-approximation. It's an over-approximation because our rectangles went above our curve. Here's our curve for the upper half circle. Notice all the extra area I accounted for above it. So this number is a little big, right? So it's a little less than this number. But again, how much, that could be hard to find out. But luckily for us, this is just a quarter of a circle. which means if we want to find the area of the entire circle, we would do pi r squared, but we want 1/4 of pi r squared to get our exact area, which means we're going to do 1/4 of pi times, now this radius that we had was 2, right? 1, 2, which means we're going to get 1/4 of pi times 4. The 4 and the 1/4 cancel out, right? That's 4 over 4, that's gone. So our area is exactly pi, which is approximately 3.14159. Okay, we're good there, right? We can stop there. So we're pretty close, but you can see right when we get to the first decimal place, we're already off, right? We're already, well, I would say, way off, right? Even though we're not too far off, but we're definitely off. So this is what we call the exact area. Well, the exact area is pi. This is just an approximation of that pi. So we were very close, but this is a bad method in general to use every time. But this is a great method because it's a static formula that we have from geometry. But what if this curve wasn't a perfect, a quarter of a perfect circle? What if it had some, sway to it, or what if it was oblong? We couldn't use the formula for a circle. And again, this is one of those things that we can't integrate, and we won't be able to integrate, with the techniques that we cover in this course. Right? So there are some very advanced techniques to integration that we need in order to tackle even some simple functions like the upper half of a circle. So we did the 4 subintervals, and then we used our geometric formula to get the exact area. So we can see we were close. And if you do the same process with, instead of the left endpoints, but the right endpoints, and you get all your rectangles underneath that upper half of the circle, you'll see that this number will be too small. It might be like 2.7 or something like that. It'll be an under approximation. If you do it with the midpoints, you'll probably get very close to pi, but still, as you go out a couple decimal places, you'll realize you're off by just a little bit. You're not getting the exact answer. So that is the main takeaway from 4.2. 4.2 deals with functions that we can handle geometrically, but introduces the concept of using the integral as area. And then when we get into 4.3, we will actually use the integral on some much heavier functions. I say heavier functions, don't worry, they won't be too bad. But just to give you a small taste, if we want to find the area under the curve of y equals x squared from 0 to 2, that would ask us to find the area underneath this parabola shape from 0 to 2, which we all know if we plug in 1 and square it, we get 1, but if we plug in 2 and square it, we get 4. And so when we try and find this area, and we can do the other side, but we're really concerned with finding this. Now, you're lucky in that the bottom is flat because it's the x-axis. This is flat because we're just chopping it off with this vertical line, but this is not flat. And so you cannot use a triangle formula on this thing. This is not a triangle. To exaggerate the shape a little bit, right, it has a curve built into one edge. I'm over-exaggerating the shape, but just to show you what I mean. Like, we don't know the shape just standard geometrically. And what if this isn't a square? What if it's a cube? Right? That curve is even steeper. Or what if it's x to the 4th, x to the 5th, x to the 6th? They're all different. They all have a different side over here, so they're all going to have a different area. So we don't want to memorize a formula for every power. We want to be able to calculate it. And that's where 4.3, the next section, will come in. We'll start looking at integrals like this. Right? We will integrate our square function and then evaluate it from 0 to 2 and get the exact area. That way we're not messing with rectangles anymore. So 4.2 seems a little cumbersome because it's mostly relying on old geometry and then introducing these weird approximations with these weird rectangles. Don't worry about it. As soon as we pass 4.2 and get into 4.3, it becomes much more mechanical and much more simple. Right? It's just, in my opinion, plug and chug. If you can find an antiderivative and plug these numbers in, you got your calculator by your side, you'll get a nice answer out of it. Now, if it's a weird, really weird fraction that deals with things like e or pi, then your calculator is going to leave you hanging with a decimal approximation. But if you do it by hand, it might take a little effort, but if you do it by hand, it's still very mechanical, and you'll get the exact area every time using integration. So that's what 4.3 will be on. Again, 4.3, next section, a little more mechanical. So digest this, and then it'll be a little easier in the next one. So I'll see you in 4.3.